Okay guys, this is part 2 for our example 1, and in this part we'll talk about how to calculate the maximum shear force that can be handled by our bolts. So this is for our shear in bolts. So the equation is very simple. So the maximum shear force applied must be equal or less than 0.8 Vf, which is the capacity. So to calculate the capacity, the law is 0.62 Kr multiplied by F, which is R multiplied by FUF. So Kr is actually a factor, it's a factor, length factor. You can calculate it, depends on the connection or the lab connection. And the lab connection, as I said before, it's between the first and last bolt. So you calculate this distance. It's already calculated here, 70 millimeters. So this distance, actually they call it the lab. So depends about how much space between the first and the last bolt is, you can calculate Kr, and I will show you from the code how much Kr you can get. So, and FUF is actually the tensile force. This is the tensile force for our bolts, and depends about the type of bolts that we're using. You can get how much. So, for example, we have 8.8/S bolts. So you go to table. There are table and the standard. You can check 8.8 is actually around 800. So it's basically 830, but to check it, you can go to the table and say 8.8/S for the snag type, as we say that this is type of snag, or sometimes you have a tension type. So this is snag type, which allows a little bit of uh, slip before at the beginning. So it's basically some part of your bolts gonna be slapped a little bit, but it doesn't mean that it doesn't mean that it has a less force, or it's less than the tension type. It's just a matter of slip. And I've already discussed that in the introduction about the difference between the snag type and the tension type. So let's calculate now. Let's go to the calculation. So all right, and yeah, okay, this one you can get it from the table, as I said, from here. All right. Okay, so now let's go to tension and bolts. So you go to the standard here. You can see the question, as I said, the bolts in shear is equal to 0.8 Vf, and Vf is actually equal to 0.8, 0.62 Kr multiplied by FUF multiplied by this type. And what I mean by this type, I'll show you now. What is it? What NNAC or N? This is actually the area of the thread, or the area of. This is what I mean by N or AC. So basically, you go this is the number of shear plane. So if you have only 2 plates, it's gonna be 1 shear plane, which is this one here. So this is the shear plane. So we take NX is actually the shear plane exclude in the thread exclude, which means it is in this part. It's not in the thread part. If it is in the thread part, so it is actually going to be in the NM part. So basically, you have AC. AC means the area of the bolt in this part, and AO is the area of the thread part. All right. So this is different. So for example, you having only 2 plates. So basically, it's going to have only one plane, and this one plane should be decided whether your plane is actually in the thread part or in the other part. So to be more conservative, we usually take it as a thread part, because the thread part having a less area, and that makes it like more conservative in your design. So this is how it. So you go here. Now we'll go to our calculation. All right, so this is the equation, very simple. You just apply the equation and that's it. I will show you KR. This is KR. So KR is the length factor for lab connection. So it depends. It's 1 if our lab connection is less than 300 millimeters, and in our example we have only 70, so it's going to be 1 in our case. If it is more than 300 and less than 1300 millimeters, so it's going to have this equation 1.075. You have to calculate it, minus LJ, which is in our case is 17 millimeters. But as to go to use the equations must be for above the 300, maybe 400. So you're gonna put 400 here, 1.075 minus 400 over the 4000, and you get how much is KR, or 0.75 if it is more than 1300 millimeters. So this is actually if you have 1400, something like that, between the first and the last bolt, as I've already shown. So if the distance from here, like for example, if you're having more bolts here, more bolts here, and then you calculate this is the last bolt, you calculate the distance from here till here, and you find that okay, this is actually 1350, like okay, so 1350, which is more than 1300, which goes to the third, like KR is going to be 0.75. So this is how you basically do it. And for FUF, which is here the last part, so you go to your type. So your type is 8.8/S. So you go to table 9.3.1 in the standard. By the way, I'm talking about the Australian standard. It's Australian New Zealand standard is almost the same. And if you go to any other standards, like for example American standards or European standards, you're gonna have these tables, but might have different numbers, depends about what they're using. But it's the principle are the same, and the calculation is sometimes different in the factors. Like here we're using 0.8, 0.62. These factors might be different. The equation might be a little bit different, but you're gonna have almost the same and near values. So in our, as I said, we have 8.8/S, which is around 800. In our part, we have 830. So this is FUF, 830. So using here in this equation, you will have 830 here, 830, and the KR you have 1, and you're gonna use, as I said, this NN. You're not gonna use it. You're gonna assume make your design more conservative and use the threading area. So you're gonna use your plane here in the NX1, and AO is going to be from the table. So you go to the table of your boards. Your boards are using M20 in the question. So you go here, the size M12, M16, M20, M24, M30. So this is from the standard. So you go M20, and then you go, okay, so which area you're using? Do you want AO or you want AC? So basically, well, okay, I'm sorry, we're using AC because AC is actually for the thread area, and then AO is for the area, the shank area. So this is actually we're using. So we're using the bolt minor area. Okay, so we're using AC, and the N we're using is NN. So NN, the number of shears with the thread included. All right, so we're using this part. Let's go to. Okay, so we're using this part, right? NN. NX going to be 0 in our part because we are assuming that the plane between the two blades in our bolt is going to be in the thread area, which is going to thread included, and we're going to use AC as a smaller area. All right, so we go here in the table. We go to, you can see here from, okay, LO, let's get M20 314. However, for AC is going to be 225. You have 235, but we're going to use 200. The less area is 225. All right, we make more conservative our design. So we're using this area 225, and you can see that there are difference between the shank area and the thread area. So to be more conservative, you use the small area. So that means the nx is going to be 0 and nn is going to be 1. All right, nx is going to be 0 and nn is going to be 1. All right, so let's apply the equation. So this is basically the equation. No, that's here. All right. Kr, as I said, is going to be 1 as we have less than 300, which is 70 millimeters only have in our example. And FUF is 330 from the table, we got it, as our type is 8.8/S. And we go number of shear in the plane. How many numbers in the shear? As I said, there are only 2 plates, so the number of planes or shear planes is actually the number of plates that we're having minus 1. So 2 plates means you only have one shear. So assume the thread, we're going to assume that the thread are included, which is the more conservative. The NN is going to be 1, NX is going to be 0, and AC we're getting from the table 225 for our M20. All right, it's from here, M20, you get 225. And if you're using the another area, which is OA for the shank area, is going to get 314, which means your design is less conservative. However, we want to make the worst case scenario, and we're taking the less area. So even I wrote here the area of AO to make like to show you the difference, that there are a huge difference between both areas. So using this one, the smaller area, to be more conservative, and that's how we calculate it. You just apply the formula 0.8 multiplied by 0.62 multiplied by 1 multiplied by 830 multiplied by 1 multiplied by 1 multiplied by the area, and then you divide it by 1000 because of the units conversion to get how much kilonewton per bolt. So each bolt, how much is going to be carried. So this is how you got it for each bolt. So you can also calculate how much all the bolts is going to be carried. So this is actually VF, and then apply the factor of safety, which is 0.8 here, and you got how much bolt after factor. And then you have to get how much load it can be the N carried, so you multiply by the number of bolts. This is actually making an assumption that our plate is rigid, which means that in all the bolts, the distribution of the shear force is going to be the same. So for example, let's go to the question. I explain it a little bit. Okay, so as we having here, so I assume that the both plates, these plates, are rigid, which means the load here, if it is like the load at N, so it means N over 4 is going to be carried in this bolt, and this bolt also is going to be N over 4, and this one is going to be N over 4, and this one is going to be N over 4. So this means we assuming that there's no deformation in our bed, and this is actually why I assume that, because when we design, we make an assumption that the plate is going to be much more stronger than the bolts. So this is why we're assuming that it's going to be a steady deformation in our design. So to get how much N, so you just apply, we got 92.6 for each bolt, so multiply it by the number of bolts, and we get how much shear force can be carried, and you can see like 370. However, when we calculate how much tension can be carried in blade 1, we get 428, and we do the same and calculate the tension for blade 2, we get 500. No, wait, here we got we got 428, and here we got 457, and then we take that for the tension, we can actually carry 428, which comes from the first plate. All right, so and then when we calculate now the shear, we found like, all right, the bolts can only carry 370. This means if we designing for this situation, and we say okay, that we just calculate for the tension and said that the N can be 428. This means the boss is gonna be fell before the blades fell, and this is a problem. So you have to say calculate all the things that inside um, can be inside our situation to get what is the maximum force that can be applied in the steel connection. And this is actually part two. We're going to part three after that about the tension in bolts. And we don't have any tension in our bolts in this situation. So we'll skip this one for other examples. Maybe we'll find it. We'll also go to the bearing and tearing. We have a bearing and tearing, as I said before, in our plates might occur, and we'll calculate this bearing and tearing, and then we'll go to calculate the bolts in combined, because we're having now tension and shear. However, we don't have tension, so this part also it won't be exist because we don't have tension in our parts. And in other example, I'll describe when we have tension in our parts and how we can. So basically, the tension in part. Let's say this is our bolt. So the tension when you have an axial force, almost axial force to the section. All right. So when you have an axial force in here to the section, then you have a tension in the bar. So when you have a tension, basically this can be in when you're having some moments inside. All right, so this is bar two. I will end it here, and we'll go to bar three.